Hey, everybody. Thanks for joining us. We're going to be talking about SlateDB, which is a cloud-native LSM built on object storage. The talk will cover the architecture of SlateDB and some of the interesting challenges and trade-offs we had to make when building a zero-disk architecture. For starters, I'm Chris Riccomini. I'm an investor, engineer, and author. I've worked in open source on Apache Samza, which is a stream processing system, Apache Airflow, which is a workflow system, and most recently, SlateDB, which is the key value store we're going to be talking about today. We opened that up, Rohan and I, along with a few others, and have had a lot of traction with it. Rohan, on his end, is a co-founder of Responsive, which is a Kafka Streams stream processing system. He's ex-Confluent and Yahoo, and has worked on a number of open source projects as well, including KSQLDB. So the plan for today's talk is we're going to give you a little bit of backstory about SlateDB and its motivation, talk about some of the features, and dig into its architecture, and wrap things up with a few basic performance numbers. It's a little early, but we'll give you some details about what we're seeing so far on the performance side. So I first came across this concept of zero-disk architectures through WarpStream, which is a Kafka sort of replacement system that's Kafka-compatible protocol that stores all of the events in S3. And I was really fascinated by this. I thought it was kind of a brilliant idea because it addresses a lot of the traditional challenges you see when you build a distributed system around dealing with consistency and durability and so on. This approach has since kind of taken off. There's a system called TurboPuffer, which is a vector search system that's built on top of object storage. There's Neon, which is a Postgres database that stores all of its page data in S3 as well. TIDB has recently gone serverless with object storage. And so the question is, like, why are people doing this, right? I mentioned you get a lot of benefits from S3. So on the durability front, you get 11 nines of durability, I think is what AWS offers. In terms of scalability, you get a ton of scale. I think they do something like 280 trillion objects a day, 100 million requests per second. So they can definitely handle your workload. And then availability-wise, just their basic buckets will give you 4 nines of availability. Some of the other buckets out there, like from GCP, for example, have multi-region or dual region that can even do better on that. So it really simplifies the architecture if you can sort of ditch the traditional, disks or EBS style storage systems and leverage the replication and scalability that object storage provides. So I started noodling about this a little bit and thinking through some of the trade-offs. And I kind of came up with this model that gives you 3 knobs that you can turn when you're working with a zero-disk based architecture system. The first is cost. So the more writes that you send to object storage and the more reads you get, the higher your API cost is going to be, because AWS and the other cloud providers bill you on a per 1,000 request basis. The second characteristic to consider is latency, which is like how long your write or read is going to take. And the third is durability, which is essentially like, is your data making its way to object storage and you're notified of it? And so you can kind of pick and choose which of these things you care most about. So there's a really nice sort of flexible interplay here with zero-disk-based architectures, where if you don't want to spend a ton of money, then you can kind of pick between higher latency or lower durability. If you're willing to spend more money, then you can get both low latency and better durability. And so essentially, in a high cost environment, you're just going to send every write directly to S3. And the latency you're going to wait for is essentially how long it takes to write to object storage. However, if you care about cost, then you kind of have to pick, do I want to batch writes together? In which case, when you write, you're waiting not only for your write, but for there's a time window where you're going to wait for other writes to come in. And then you're going to send that whole chunk of writes as a single put into object storage. And that amortizes the cost of a single API put across multiple across multiple key values in our case. Lastly, you can do durability, where you can do that same batching, but you just don't wait for the response. And the idea there is that some systems don't really care about durability, or they have a persistence layer ahead of something like SlateDB that can handle the durability for them. So I kind of tried to dig into this a little bit in a blog post called the Cloud Storage Triad. And I kind of described what I just told you and sort of looked at some of the other systems that are out there and how they're implementing it. And then I pitched the idea for SlateDB in this blog post. And started hacking on it a little bit. And I was surprised to find there's not really anything out there quite like SlateDB. There are some systems that try to use object storage, such as RocksDB Cloud, but they're not pure object storage, zero disk based. A lot of the implementations I mentioned earlier, WarpStream and TurboPuffer and so on, have implementations, but they're not open source. And so put out the pitch and got a lot of people and a lot of interest. And so we started the project. And we decided on a fairly ambitious architecture and a series of philosophies that we've adopted when we're building SlateDB. So we built it with the idea that buckets will be multi-region, low latency, and had support atomic compare and swap. And so some of these things like don't yet exist or don't yet exist in unison. For example, at Google Cloud, you can get multi-region buckets or dual region buckets. With S3, you can get S3 Express low latency. S3 just adopted compare and swap. So now all the major cloud storage providers provide compare and swap, which is essentially a way to do an atomic write. And if another writer tries to write to the same file, you can detect that and prevent it. So the point being is that SlateDB is built with the belief that eventually most, if not all, cloud providers will provide buckets that address many or all of these things. But it's a long-term goal. So some of these things, depending on your cloud provider, might be missing. So let's talk about just the SlateDB features and use cases. First off, SlateDB is a in-process Rust library. So there's no network protocol or remote connection or anything. Everything resides within your process. It's a key value store, which looks a lot like RocksDB, if you're familiar with that. Unlike RocksDB, all the writes go to object storage, which I mentioned. That's sort of its claim to fame. And it's implemented as a log structured merge tree, which is sort of one of the two standard ways for building a key value store, the other one being B trees. And the case for log structured merge trees is there's essentially like an append only log where you periodically compact out duplicate writes to get only the latest version. And Rohan will go into more detail about that later. In terms of features, I mentioned it's zero disk based architecture. We support single writer only, but multiple readers. The multiple readers can also exist on different machines, although that is not yet implemented. That's in the plans and the architecture supports it. We support both in-memory and on-disk read caching. In fact, the on-disk read caching, I believe, is getting merged in today. On the single writer side, we've built writer fencing, and this is using that compare and swap operation that I mentioned earlier. And the idea here is that if you have your process and you're writing to a database, SlateDB database, and then it fail or think you failed and start a new writer for the database on another machine, SlateDB is smart enough to detect that there might be two writers writing to this single database, and it will fence out one and prevent writes from corrupting the database. In the future, we want to adopt snapshots and transactions as well. That I think should allow us to support some OLTP use cases. And then lastly, pluggable compaction. Right now we have a size tiered based compaction, and there's a great design doc that describes that. But compaction is one of those things that's sort of a never ending endeavor. So I anticipate we'll have different compactors for different workloads. On the use case front, right now we're pitching it for people that are willing to tolerate a little more latency, sort of in the 50 to 100 millisecond range. Alternatively, if you're willing to lose some data or are willing to pay for API puts, it's a good fit for that too. And I think these sort of loosely correlate to that tweet that I had showed earlier, where it's durability, cost, or latency, right? And so the fits that we found early and the interest that we've seen come from stream processing. Serverless functions is another one because there's a zero disk base. You can actually run it without any disk. On the durable execution front, they depend on transactionality. So they're interested, but kind of waiting for the snapshot and transaction features. And there are many other cases. I think long-term, we'd like to support OLTP as well. But until we get that snapshotting and transactionality, and I think that's a little bit farther out. So with that, I'm going to turn it over to Rohan, who's going to get to the meat of the architecture and talk about performance.
All right, thanks, Chris. So in this next section, I'm going to talk give you a high-level look at SlateDB's architecture, just so you can get an idea of how it works internally. So as Chris mentioned, SlateDB is a single writer, multiple reader, diskless LSM on object store. LSM stands for log structured merge tree. LSMs are a good fit for object stores because they kind of sidestep a lot of the inherent drawbacks that object stores tend to have. Namely, object stores typically have a constrained API, so they can't do random writes, and LSMs will only ever write immutable objects, so they don't have to deal with random writes. And object stores also tend to have very high API costs. So with an LSM, you can sidestep that, at least for puts, because they batch writes, so you can amortize the cost of a single object store put over multiple puts in the SlateDB. So now I want to dive into how SlateDB lays data out on object store, starting with what we call the manifest. So the manifest contains all of SlateDB's metadata. So this includes, primarily a list of all the other object store objects that make up the database. Each of those objects is an SST, which stands for sorted string table, which is basically just a big list of key value pairs that are ordered by key. It also encodes the structure of how those SST objects comprise the log structured merge tree structure. There's also some snapshot metadata. And then finally, there's a writer epic in there, which we use to ensure the single writer property and prevent multiple writers from clobbering the database. Now, physically, that manifest that I described is laid out as a series of objects that are write once versions. And we ensure that each version is write once by using the compare and swap operators offered by object stores. So if you wanted to make a manifest update, you would read the latest manifest version, make your update locally, and then write it out using compare and swap to the next version. And if that compare and swap fails, you can just go and reload the latest version again and apply the write. Now we come to the actual data stored in the database. So this is broken up into a wall subtree and a compacted subtree. So the wall contains SlateDB's write head log. So the wall is also a series of write once objects, except this time each object is its own wall entry that contains the set of key value pairs that were inserted into the database at the time that wall entry was produced. Now, over time, SlateDB will compact that wall into the sorted runs that are compacted to minimize space and read amplification. So the data in compacted is organized as a series of sorted runs. So a sorted run is basically a big set of key value pairs that can span the whole key space of the database. So at the head of that list of sorted runs, we have what we call L0, which is a series of single SST runs, where each run is made up of a single SST. And then we have the true sorted runs, where each sorted run is broken up into multiple SSTs to keep the metadata pageable. And those sorted runs are maintained in insert order so that it makes lookups a little bit easier. So now I want to come to how the writer works. So the writer is the thing that sits on top of object store and actually implements SlateDB's API. So the writer is totally diskless in the sense that it doesn't store any of its critical state on local disk. Everything is kept in object store. It can use a disk as a cache, but it won't store anything that it needs to be durably stored in that cache. So the writer, when it accepts a put, will first add that put to an in-memory wall table. And then every flush milliseconds, that wall table is frozen and added to a queue of immutable wall tables that are then in the background written out to wall objects in that wall subtree in the object store. If you're a client, you can ask SlateDB to make that sort of that latency and durability trade-off for you. So you can ask for the put to have really low latency, in which case it'll be acknowledged immediately after the put is added to the wall. The drawback there is then that you don't know that the put was durably written at the time of the acknowledgement, or you can choose to wait longer and have the put acknowledged only when the immutable wall is written durably to object store, at which point you know that the write is durable. We also do that first level of compaction from the wall into memtable from the writer process itself, just to distribute some of the compaction load between the writer and the compactor. So the way that works is that once a immutable wall table is written durably to object storage, its data is added to another in-memory table that we call the mem table. And that when that mem table reaches a size threshold, it defaults to 64 megabytes. It's frozen and added to a queue of frozen mem tables that are written out to the L0 files under a compactor. All right, now we come to reads. So today, SlateDB only supports point reads, so we're working on range scans. The way that point reads work is they just look through all those data sources that I described in order. So starting with the wall, then the immutable walls, then the mem table, and the frozen mem table, and then all those sorted runs under compacted. And it'll look for the key that was requested in each one of those, and when it finds it, it terminates the search and returns the key back. And we use Bloom filters and all the L0 and SR objects to help us prune that search. When we do have range scans, the way that that'll work is we'll have to do the range scan in all the data sources and then sort merge the result back. So the other major process that SlateDB runs is the compactor, which does the work of compacting the data in that compacted directory to reduce space and read amplification. The compactor is designed to be totally decoupled from the writer. And its only way of communicating back and forth with the writer is via the manifest. So this kind of frees you up to run the compactor on separate resources, though by default it runs in the same OS process. The compactor itself is made up of three components. So there is the orchestrator, which does all the work of sort of managing the compaction process. There's a scheduler, which implements the compaction style that SlateDB uses. And it's pluggable. And then finally, there's an executor, which actually does the work of taking a bunch of source sorted runs, reading all their data, sort merging, and writing out a single consolidated sorted run. So the orchestrator, its job is to periodically synchronize all the manifest updates from the writer so that it can discover new L0 objects. And then it gives this information to the scheduler, which then decides what compactions need to be run. These are returned back to the orchestrator, which then goes and instructs the executor to run them. The orchestrator will monitor the process, and when they complete, it'll go and update the manifest with the new database metadata that reflects the result of the compaction. The scheduler, like I said, is what implements the compaction style. Today, we support size-tiered compaction. So the way that scheduler works is that it'll look for consecutive sequences of sorted runs and are compacted that are roughly the same size, and it'll specify compactions that merge those together. But because it's pluggable, it's very easy to write new compaction styles, or if you're using SlateDB and you have some style that's like really, or that would work well for a specific use case, you can pretty easily plug in a different policy. Lastly, there's the executor, which goes and does the actual work of merging sorted runs and writing out the compacted sorted run. Right now, that runs directly in the compactor process, but it's also pluggable, so we can support other executors. So, for example, if you want to take a really heavy compaction and run it on a spot instance that has a bunch of resources but is short-lived, you can do that to keep costs down. So yeah, that's a really high-level look at how SlateDB works. If you want to dive deep into some of the more gory details, we have a link here that points you to our design docs, and those go into a ton of detail on how everything works. So in this next section, I want to touch briefly on performance and some of the benchmarking we've done. We don't have a thorough set of benchmark numbers yet, just because SlateDB is such a new project. Like, we just started it a couple months ago. What we have done is gone and tested some of the more critical subcomponents to make sure that they're performing the way we expect. So the first thing that we tested was the wall writing and fencing protocol to make sure that it would give us reasonable latencies with high durability and good cost. So we simulated on a T2 2x large instance, and with a kind of typical flush millisecond setting of 5 milliseconds, we're seeing latency on the order of tens of milliseconds. So that's kind of explained by your put has to wait for that wall to be frozen, which takes on average 2.5 milliseconds, and then the write has to be written out to object store. The other thing that we spent a good amount of time optimizing was the compaction execution process. So like just taking a list of sorted runs and doing the work of sort merging them and writing out a resulting sorted run. We benchmarked that on kind of a general purpose instance in Amazon, so in 5x large, and we were able to saturate the available bandwidth between that node and S3 with 2 parallel compactions. Lastly, I just wanted to kind of point you to some resources if you're looking to get started with SlateDB. So if you'd like to start using SlateDB for your projects, you can head over to slatedb.io, and there's a ton of good resources there to help you get started. And we also are, love to get new contributors. There's a ton of cool stuff to work on. We need more language bindings. There's some good performance benchmarking work, new compaction schedulers, snapshot reading, all kinds of things. So you can head over to our GitHub, where we have a pretty well curated list of issues that you can look and see what needs to be picked up. So that'll wrap things up. Just wanted to thank everybody for listening. And if you'd like to get in touch with either of us, you can find how to do that here.